If you look at the third tab on your prep file, you'll see that we need to conduct a linear regression in order to predict the number of passengers based on the length of a cruise ship. In order to conduct that analysis, I am going to open my data analysis tool pack. I'm going to select regression and hit OK. We're going to need to select the data for our y and x variable. So the y variable is the variable that we want to be able to predict or estimate, and we want to be able to predict or estimate the number of passengers. So I'm going to select that data, including the heading. Our x variable is the variable that we're using to predict y. So that would be the length of the cruise ship. So I'm going to select that data, including the heading. I want the box checked for labels. And then for my output range, I'm going to select the designated cell. And you can see that it's right here. I'm going to hit OK. OK again. And here is the output from the regression analysis. So first we need to do the p-value approach for the global test. Here's the p-value. You can see that it has this E negative 53. This is scientific notation. So this means that this is actually a very, very small number. That E negative 53 means that you need to move the decimal place 53 spaces over to the left. So the actual value is 0.0000, so 53 zeros, and then 2944. So this is a really, really small number. Anytime you have a p-value that's less than 0.001, we report it like this. So it's less than 0.001. Remember, if the p-value is less than or equal to 0.05, then we can conclude at least one of the x variables significantly predicts y. And we only have one x variable, so that's length. And you can see that the p-value for the test for the individual coefficient is the same. Again, in simple linear regression, it's always going to be in agreement. You're going to have the same p-value. Since our p-value is less than or equal to 0.05, we can conclude that length significantly predicts the number of passengers on a cruise ship. Now I'm going to return to the questions, and we're asked the p-value for both the global test and the p-value for length. And if you remember, it was less than 0.001. Whenever you have a p-value that's less than 0.001, you should report it as less than 0.001. So on the assignments, don't click on the cell for the p-value. Actually type in p is less than 0.001. The answer to question number 3 is yes. And again, because our p-value is less than or equal to 0.05, we can conclude that length significantly predicts passenger capacity. The next question asks about the regression equation. If you return to your output, we can figure out what the regression equation is. If you remember, the equation is y hat, or the predicted value of y, so it would be predicted number of passengers, equals the y-intercept. In our case, that would be negative 20.30, plus the slope, which would be 4.77, times the x variable, which is length. So that is our regression equation. For question number 4, that would be option C. Now I'm going to complete the model summary table. And to complete this, I am going to reference the cells in the output. So first I'm going to indicate what the intercept is. And the slope for the length. The p-value for the length. Actually, I'm not going to reference the cell, and that's because it's less than 0.001. So I'm going to report it as less than 0.001. Now what I want to do is I want to use the regression equation to predict the number of passengers. So I'm going to use my regression equation. So it would be equal the y-intercept plus, and then in parentheses, the slope times length. I'm going to use absolute referencing for my y-intercept and my slope because I want to copy the equation down, and those are not going to change, so I'm going to want to lock them. So you can see the estimated number of passengers, and remember this is in the hundreds. The purpose of regression is to be able to predict or estimate something. So we want to be able to predict the number of passengers. But we know that the regression equation isn't going to provide this perfect prediction. So it's not going to get the number of passengers 100% accurate every single time. So there's going to be some error associated with our regression analysis. There are statistics that you can look at that will give you an idea of how much error is associated with your regression equation. Before I talk about those statistics, I want to elaborate a little bit more on what I mean by error. Another term for error is residual. Error or residual is the difference between y and y hat. In other words, it's the difference between the observed or actual value of y and the predicted value of y. Here's a visual depiction of error. If you focus on this dot right here, this is a restaurant, and their website hits were about 1,450. And their weekly revenue, or their actual value of y, was about 11,500. However, you can see that the regression equation predicted that their weekly revenue, or predicted the y variable, would be about $13,000. So again, this is the regression line. It's the predicted values of y. So this difference between the actual value of y and the predicted value of y is called error. For some observations, there's not that much error. So if you look at these restaurants right here, you can see that their actual weekly revenue was very similar to what the regression equation predicted. However, for other restaurants, there's a much greater degree of error. So if you can look at this restaurant, you can see there's a lot of error. Their actual weekly revenue was a little over 10,000, but the regression equation predicted that it would be a little over 12,000. So the regression equation drastically overestimated how much weekly revenue this restaurant would have. The output provides a statistic that's called the standard error of the estimate. This will give us an idea of what our average error is. So it'll provide the average difference between y and y hat. Ideally, we want this value to be small. The smaller it is, the less error there is. If you return to your prep file, you'll see that the model summary table asks for the standard error. I'm going to reference that cell. This is the standard error. So our standard error is 4.55. This means, on average, the actual number of passengers on a cruise ship will differ from the predicted number of passengers by 4.55. And remember, the data was in hundreds, so this really means that our average error is going to be about 455. It's really important to look at the standard error and see if you're comfortable with the average error associated with your predictions. Just because you can use X to predict Y doesn't mean that you would actually want to use it in real life. So if this number, 455, is too big of an error when it comes to estimating the number of passengers, then the researchers would want to use another variable or maybe a combination of variables to predict the number of passengers. They might want to include other variables in a multiple regression analysis, and they might see that standard error decrease. Another useful statistic to compute is the 95% prediction interval. This is an interval or range in which we are 95% confident that the actual value of y will be included in. To determine the lower limit of the range, you take y hat minus 2 times the standard error. To compute the upper limit, you take y hat plus 2 times the standard error. If you return to the prep file, you can see that we're asked to compute the 95% prediction interval. So to compute the lower limit, I'm going to take y hat, or the estimated number of passengers, and I'm going to subtract 2 times the standard error. I want to copy this function down, so I'm going to lock the standard error. To get the upper limit, we'll take y hat, or the estimated number of passengers, plus 2 times the standard error. The 95% prediction interval is giving us a range in which we are 95% confident that the actual value of y is. So for example, for the first cruise ship, we are 95% confident that the actual number of passengers will be between 3.97 and 22.16. For the second cruise ship, we are 95% confident that the actual value of y, or the actual number of passengers, will be between 8.74 and 26.93. The last statistic I'm going to discuss is r squared. If you remember, r is the correlation coefficient, so r squared is just the square of the correlation coefficient. This statistic will tell us the percentage of the variance in y that can be explained by the variance in x. This may sound a little bit complicated, but remember, variance is just giving us an idea of how much differences or variability there is in that variable. So r squared is telling us the percentage of differences in y that can be explained by the differences in the x variable. We want our r squared to be a large number. The bigger that it is, the more accurately we can predict y. Question number 5 asks about r squared. To answer this question, I'm going to reference the cell. Here's r squared. It's 0.78. So this means that 78% of the differences in the y variable, or the number of passengers, is due to the differences in the x variable, or length. So why do cruise ships have differing number of passengers? Why can they hold different amounts? 78% of the differences between cruise ships in terms of how many passengers they can hold is due to their differences in length. So you can see that number 6 is essentially asking what r squared is, so I'm just going to type in 78.06. The last 2 questions ask about the standard error of the estimate, which we already determined. If you remember, it was 4.55 if you round to 2 decimal places. The last question is also asking about the standard error. Again, standard error is the average difference between the predicted value of y and the actual value of y.